Hey guys, back for another video. So my name is Oscar Savalainen, in case you don't know me if you're new to the channel. I do a lot of AI stuff and a lot of neural network quantization stuff in particular. And this video is part 3 of 3 where we take a publicly available ResNet model and we do FX mode quantization on it. In this video, we're actually not going to talk too much about the specifics of a ResNet. We're not going to talk even that much about quantization, actually. It's mainly just going to be about navigating the graph and getting used to, not the quantization aspect of FX mode quantization, but getting used to the FX part, which is the kind of graph part. So I'll just give a quick background to what FX quantization is, which is, and I'll try to speed through this. So at PyTorch, they're the very nice, clever people at PyTorch. They have in recent years they've started putting out graph-based optimizations for PyTorch models just to make them go faster, to make us be able to automate a lot of stuff in quantization, to be able to kind of compile a model and ship it to external, edge devices, whatever. All of that is much easier to do if you can work on something called a graph. So particularly a directed acyclic graph. And in those directed acyclic graphs, in that representation of a neural network model, you can do all sorts of optimizations that are really hard to do in kind of vanilla PyTorch. Because vanilla PyTorch just kind of runs in something called eager mode. It makes it super easy to do experimentation and to kind of try out different things, but it makes it a nightmare if you're trying to do computational optimization. So the very clever people at PyTorch is kind of they found a way to have the best of both, and that's kind of PyTorch 2.0. But part of that is kind of FX mode quantization, and that's when we quantize a model. Now, before we had to use something called eager mode, we had to place all of these kind of quant stubs ourselves, flow functionals ourselves, we had to fuse modules ourselves, we had to be really careful with stuff. Not with FX mode. FX mode takes care of everything for us, it's beautiful. So in the previous 2 videos, that's what we were doing. We took a ResNet model, we quantized it with FX mode, and then in the second video, we kind of looked a little bit how quantization specifically plays with the graph. Today's video, we're just going to be doing more advanced graph-based manipulation. So we're going to be traversing the graph, we're going to be swapping out nodes. So that's what we're going to be doing in today's video. So yeah, if that's interesting, keep watching, and I hope you enjoy the video. Okay, so if we get into the code, this is just the code from the previous 2 tutorials, but I've cleaned it up a little bit. So yeah, here we initialize our ResNet model, we define the qconfigs, we do the qconfig mapping, we assign specific qconfigs where we know the number of out channels so that we can have learnable qconfigs for the weights, because we need to have access to this attribute of the number of out channels. And then we create an example input, and then we do prepare QAT FX, which does 2 things. It does the symbolic tracing, and it simultaneously does all of the quantization. It puts in place all of the qconfigs, all of the quant stubs, all of the flow functionals. It does all of our fusing for us, which is amazing. We love it very much. And then we just evaluated the model. We evaluate the original model, we evaluate the FX model, and then that's where we basically left off, and we kind of looked at okay, printing out the graph and what that looks like. But today, we're going to do some more, as I mentioned, we're going to do some more kind of advanced graph-based techniques, and I'm going to show 2 things. One is this graph iterator storage class. And this is, I'll get into this in more detail, but it's quite a sophisticated piece of code. I think it was in the Torch FX documentation that I came across it. And then I kind of edited it a little bit for my own use case and kind of made it a bit more generic, but we'll be going over that piece of code because it's quite cool. And then the second thing I'm going to show you is how to swap out nodes. So specifically, we're going to be swapping out conv BatchNorm ReLU layers with just conv ReLU layers. We're going to be fusing in BatchNorms into the preceding convs, but I'll talk more about that later once I get to it. But we're going to start with this graph iterator storage thing, just because I think it's pretty cool. So to give full context as to what this does is that it basically, what it does is that it iterates through the graph node by node. So if we go down here, this is basically what it does. It goes through the graph node by node, and then depending on what kind of node it is, like if it's a placeholder, there's just the input to the graph. It'll just kind of call next, and all of the point being that for all of these different kinds of nodes, the node can be a function, it can be a method, it can be a module. It doesn't matter. each line of code here is responsible for basically returning the output activation of that node. So this looks super complicated, and it is super complicated, but that's kind of the reason why I show it, is because I think this piece of code, probably more than anything else I've seen in the documentation, really shows you in one place all of the different ways that you can kind of manipulate the graph, how you can kind of call, each node to get the output tensor that you want to get. So I think just analyzing this code and kind of like looking at it deeply is a really good way to kind of understand how all of these different nodes work and the kind of different operations that they're performing. But this piece of code, this graph iterator storage, doesn't merely iterate through all of the nodes, because, I guess I'll go back to the beginning. So the way you begin is that you just feed it in an example input. So this example input, in our case, is just a random tensor, but it could be any data that you wanted to feed through it. And then, it's going to iterate through the graph. So for each node, it's going to start with this placeholder, and it's just going to get the result. The output activation of the placeholder node is just the input. There's nothing particularly special about this. But depending on which node type it is, what kind of operation it is, it's going to call something specific. So if it's a get attribute, it's going to call fetch attribute on the node target, and that will represent the attribute in question. If it's a function, it will do this kind of unpacking of the node arguments and the node keyword arguments, which is kind of cool. And then it will call the target respectively. So in this case, the target will be the function, and then these will be the inputs to that function. There'll be the arguments to the node and the keyword arguments of the node. So I think that's kind of cool, and you can kind of get an intuition for how that works. And I'm actually going to run this because I think it would be easier, because then we can look at examples in the graph. Call method is similar. It has to do a little bit of extra unpacking to get access to the method. So it unpacks by calling this load arg function, which is kind of described up here. Quite a complicated piece of code. But, again, I don't show this to you because it's easy. I show this to you because it's complicated, and I don't fully understand everything that's going on here. But I do think that this is like good code. If you want to become good at like navigating the graph and understanding how it all fits together, I think this is like a pretty useful piece of code for that. But it extracts the method, and then it'll load the coargs as well. And then it'll do this similar kind of get attribute, but in this case it's calling the method on the node target, and then it's doing this unpacking of arguments and keyword arguments. Similar thing going on for call module. And self in this case is our model. This is like our entire, graph module. It'll access the modules, it'll find the one in particular that we care about as far as the kind of modules are concerned, which is stored in this node target, and then again it does this unpacking of arguments and keyword arguments. Okay, so we get a rough idea of how each one of these different nodes work, and how you can kind of manipulate it so as to get the output tensor for a given input. But something that then, just iterating through the graph itself and kind of feeding data through it iteratively isn't super interesting. I mean, it might be, maybe you're super interested in it, but what's cool about this is that we can actually intervene with whatever function that we want to. Because like in this case, we're getting access to the result and we're getting access to the node, and we're going to do something. So, and what we're going to do is basically defined by this function that we feed in while we're setting up the graph, while we're initializing the graph iterator storage. And in our case, this is kind of what this function does. So just to back up a little bit, if you're familiar with PyTorch models, you might be familiar with something called, hooks, like forward hooks or backward hooks. And this is basically the same thing. So a forward hook and a backward hook, it's basically a kind of a function that you can insert into your model at a specific place, and it'll get triggered when there's a tensor being fed through the model. So in the case of a forward hook, when you have a tensor being fed forward throughout the model, that hook on a module or on a layer will get triggered when that tensor gets to that module. You can have a pre-forward hook or a post-forward hook, depending if you want the hook to get triggered before the data gets fed through the layer or after the data gets fed through the layer. You can also have backward hooks, which work the same way, but they only work on the back-propagated gradients. So they only get triggered in a backwards pass for the model while you're training, which is super cool. But let's say for whatever reason you don't want to put hooks inside your module, we can actually do it in a different way now with this graph model, which I think is super cool because I love hooks personally. So you can think of this function which where, when we initialize, we are setting it, as our self-storage function, but this doesn't have to be called storage. This could be called anything arbitrary. And we're calling it after we get the output tensor for every single node. And then we're doing the self-storage. So you can basically think of this as a post-forward hook. If you put it at the top here, it would be a pre-forward hook. I'm not sure how you do this with backwards hooks, but anyway. And what this hook is responsible for, or this function, is that it literally just takes the shape of the intermediary output tensor of the node, and it takes the data type, and it stores it as attributes of that node. And then once we're done feeding data through the model, we can access it. So we can iterate through all of the nodes, and we can print its name, shape, and data type. And that is what we see here. So it's kind of messy, but yeah, that's basically what's happening. It's that we're printing the node name, we're printing the size of the tensor being fed through it, and we're printing the data type. So it's kind of cool. It's like another way to do forward hooks. So I show it, and again, this doesn't have to be just something as generic or as bland as storing the data type and size. You could do anything with this, really. So personally, I think this is really cool, and I think if you're trying to become good with the graph, I think this is kind of useful code to study. So that is why I share it. I share it not because it is easy, I share it because it is hard. But next, I'm going to show the second kind of graph manipulation technique that we're going to cover in this video, and that is swapping out nodes. And specifically what we're going to be doing is, as I mentioned before, we're going to be basically taking BatchNorm layers, because if we go to, let's take the first conv layer. If we take this, we see that it's a conv BatchNorm ReLU 2D layer, and it still has this explicit BatchNorm layer that's getting updated as we're feeding data through the model. That might not be what we want. We might want to fuse that BatchNorm layer into the conv so as to effectively have the BatchNorm layer be static and kind of done away with, and then just have a conv ReLU 2D. So how would we do that with the graph? Well, how we do it is actually quite simple, and I'm quite a big fan of it. So I created this function, conv BatchNorm to conv, and it's going to take in this FX model. It works in place, which is why I do this deep copy. And what we're going to do is that, basically every time it finds a conv BatchNorm ReLU, it replaces it with conv ReLU. If it's just a conv BatchNorm, it replaces it with just a conv. And all that we really need to do is iterate through all of the different nodes in the graph. If it's a module, then, which is cool, because now we can do this kind of thing, we can see if it is actually a module, then we can get the module, we can check if it is the kind of type that we would like to replace, and then here we're going to have two different steps. First, we're going to initialize a new node, a new module, which is going to be a fused conv, so it's basically going to take that BatchNorm and it's going to put it into the conv, and then we're going to replace the nodes. So I'll show you how we do this fusing of the conv and the BatchNorm first. It's quite generic. Like, this is code that, you don't need to do it this way. The way I did it is that basically I initialized a new conv, or what I called new conv. In this case, it's a new conv ReLU 2D, and in this case, it's just a conv 2D. But I initialized it with all of the same attributes as the original module, the original conv BatchNorm ReLU 2D, or the original, conv BatchNorm 2D. But this now has just random parameters because it's just been initialized. And then I initialized the weight tensor and the bias tensor with the new weight tensor and the bias produced by this fusing function, which I'll discuss in a second. And it just takes in the original weight and the bias, and then it takes in the BatchNorm statistics. This is very generic code. You can find this, all over the internet. I think these equations are as old as BatchNorm is. There's also a function that you could use that kind of does this generically for you, and it just produces a conv. I just kind of did it this way. I just found, this code online first, so I just kind of copied it. But, you could also use this function if you wanted to. But yeah, so at the end of all of that, it produces this new kind of quantizable conv without the BatchNorm. And it's either conv ReLU or it's conv, but yeah, the weight and the bias tensor have been initialized correctly so that, it will have the same performance as if the BatchNorm was there, even though the BatchNorm has now disappeared. And then, once we've produced that new conv, or conv ReLU, then we replace the node module. And replacing the node module, I think, is super cool, and it's actually super simple to do. So it's as simple as, in this case, where we're taking in the node that we want to replace, we're taking in the modules, which in this case is a dict, and this is just a dictionary representation of our entire model. where the key is the name of the module in question, and then the value is just the module. And then this is the new module, which we're going to have take the place of this node. So there's really only two steps. You don't actually need this line of code for this use case. And all that we're doing is we're getting the name of the parent module, and then we're setting that parent module's attribute, which used to be, the original node, this thing, and we're setting it as new module. And that's it. That's all you need to do. There's different ways to do this. You wouldn't have to use this kind of dictionary representation of a module. You could find a way to do this with like get, submodule and then set attribute in a similar way. But it's good to know that, yeah, with literally these kind of 2 lines of code, you can just swap out nodes. And I'm actually going to show what's happening here because I think it will be informative. So if I run this again, and this won't be anything like super, informative, frankly, because we're just going to look at the parent name and we're going to look at the current name. So just we can see like what's getting triggered. And maybe we'll look at like node target and stuff. Okay, so here we are. So if we look at parent name, this is nothing. Okay, I'm not hugely surprised at that because, okay, so the one that we're currently swapping out is literally conv1. It's the very first conv1 in the entire model. So if we go, well, actually I can't go there. But generally in our FX model, if I go here, this is just the original conv, so it doesn't actually have like a parent module. Its parent module is the model itself, which doesn't have a name, so that's why parent name is blank in that case. And then if we print a node target, we can see it's also conv1. If we go to the next breakpoint, we print out name, again conv1, but this should have iterated. Okay, so now in this case the parent name is layer 1.0, which is a different conv. So if I find it, okay, so it's layer 1.0 conv1. So now we're at this convolution, which is fine because that's basically what we expect. That it's iterating through all of these convs, which are conv batch norms, and maybe with relu, maybe with not, and it's replacing them with just the equivalent fused module, which I think is really cool. So we don't need this anymore. And if we go down to the bottom, so if I exit this and I run it again. Okay, so it's done, and then if we print the transformed model, and well actually, yeah, we can just look at the conv one, right? We can see that now it's not a conv BatchNorm redo 2D anymore, it's just a conv relu 2D, which is super cool. And then earlier on we did actually, yeah, so if we now test this transform model, it does just as well as it did before. It does just as well as the layer that had the BatchNorm in it, because we did the fusing correctly. Like we updated the statistics correctly, and all of the BatchNorms are now gone, which I think is super cool. So if I go to layer, I guess it's 1, was it 0? I'm not exactly sure what I'm going to try get some module, and then if I try to access the conv, we can see that that's also equal to a conv relu 2D, which is really cool. And I think if I access conv2, then that's just a conv 2D, because before this was conv BatchNorm 2D, and now it's just conv 2D because that's got fused in. But that's it, yeah, literally. So yeah, that's all I wanted to show. I wanted to show the graph iterator storage, which is kind of a way of propagating through the graph, and then you can kind of use pre-forward hooks, post-forward hooks, however you want to. And then I also wanted to show how to swap out nodes. So yeah, that's it for the code. Hey, so that is it. Part 3 of 3 done on how to quantize a ResNet from scratch using Torch FX Graph Mode Quantization. I hope this was useful for you. Just to summarize, like, yeah, we took a ResNet model, we quantized it using FX Mode Quantization, we looked at a bit of how quantization works in the graph, and then finally we did some kind of more advanced graph-based stuff. i.e. we looked at kind of replacement for post-forward hooks and how to like store things in the model using those kind of attributes, and also how one could just literally just swap out modules, like particularly in the case which I think is quite useful, like if you wanted to fuse batch norms into the conv layer, that is how you could do it. And I hope you gained some kind of comfort and familiarity with the graph module. I know when I first started working with the graph, I was a little bit intimidated. I read all of the Torch FX documentation. I was like, I need to understand this. It is the future. But the more I work with it, the more I like it. And I hope you will feel the same way. It is kind of an important skill to have in kind of modern machine learning development, especially because PyTorch is like the most popular framework, and FX mode is becoming more and more and more important for the reasons I kind of described in the intro. So yeah, I hope this was kind of helpful to you. I hope you maybe gain some kind of comfort and confidence that you can go on and work on the graph in the future. And yeah, if you liked it, please like and subscribe. If you have any questions, please leave a comment. All of the code is available on my GitHub in the description. And please, if you have any requests for a video, absolutely let me know. Because one, I make these videos for you, so they're only useful if they're useful, right? So like, I'd like to know what you guys want. And it's also interesting for me just because I get to know what everyone else is working on. So if you have any requests, please do not be shy. And yeah, like I hope you have a pleasant evening or morning or midday, wherever you are. And yeah, see you in the next one. Bye.